Okay, so first of all, thank you for being here. It's a great honor, and I'm very excited to be here tonight. This late afternoon. And what I want to do today with you is to talk about time. So time is, in my opinion, the most fascinating of the four dimensions that we can perceive. And fundamentally, I can go here, I can go back here, but I can't invert the arrow of time. Tonight is not going to be about time travel. Maybe it will be, but not in that sense. So let's get started right away. And to get started, we need a little bit of context. And I will start off with a little tribute to the country where I originally come from. So what you're looking at here is a fresco by Domenico di Michelino. And he is showing us the universe of Dante. And here the logic is very simple. The lower you are, the worse it is for you. But the thing that is important here for me are these 7 spheres of heaven. You can see it starts off with the moon. And then we have the 8th sphere, which is the one of the fixed stars. So it's a universe that does not change. And for Dante, that represents perfection. And look here, our moon made it to heaven, thankfully, but really at the bottom of heaven. It was changing way too much, way too much. What I want to tell you tonight is a story of a universe that is all but not changing, but is not less perfect and is not less beautiful. Let's get started. I'm gonna start with a little experiment. So you're gonna be staring at 4 parts of our sky as captured by this telescope. To give you an idea of how big of these parts of the skies are, I put there our full moon. And what we're gonna watch is the results of 3 years of observations, condensed down in 1 minute and 40 seconds. And while we do so, please pay attention to new sources that come and go. Now, let's see. Right, so I hope I have convinced you that our universe is changing. So that telescope is around 1 million times more sensitive than our own eyes, to give you an idea. That our universe is changing on every possible time scale you can think of. Changing over very long time scales, cosmological ones, millennia, years, months, hours, seconds, milliseconds. There's always something that is really changing on those time scales in our universe. So what were we looking at there? To fully appreciate that, I'm gonna ask you to play a little game with me. So I'm going to zoom in and I'm gonna look at one galaxy outside. It's not our own galaxy, it's something far away. How far? 50 million light years. So the little lights that you saw appearing were all coming from other galaxies, first of all. So from this statement, you understand that they need to be extremely luminous sources. How luminous? More than 10 billion times the sun, to give you an idea. So now we have our photographer, Jason, took a picture, an amateur photographer. You can actually do it from your backyard. So he took a picture of this galaxy, which was in February 2020. And then he took another picture in May 2020, a few months afterwards. And I'm going to ask you, find the difference. Can you spot the new star there? I'm going to give you 10 seconds. Raise your hand if you see it. Don't cheat. All right. Wow, very good. Amazing. All right. So, yep, here it is. We have a new source right there. I want to draw your attention that this source here, I'm not allowed to walk past here, otherwise I will be totally there. So you can see this source here is as bright as the center of the galaxy where it was born. It's something extraordinary, something exceptional, something very, very energetic. All right, so let's go a step deeper into what were you looking at? And I showed you all of that light. As an astrophysicist, I would answer that question saying there are three main ways that can cause lights to appear in the sky. Option number one, we have a stellar disruption. Option number two, we have a stellar merger, a stellar collision. Option number three, we have a stellar explosion. As a star, I would read that title and I would think, okay, these are the three main ways I can die. Okay? So now I'm going to tell you a little bit more about each of those three. So let's start off with a stellar disruption. And I'm going to give you first a snapshot of a numerical simulation. And then I'm going to play a video so that hopefully you can get a feeling for it. So I'm a star. I am born in a galaxy, in a beautiful galaxy. My galaxy, fortunately or unfortunately, depending what you like, has a supermassive black hole in its center. I am this star, and I'm a little bit unlucky because I happen to go way too close to that supermassive black hole. And the gravity of that supermassive black hole wins over my own gravity and tears me apart. What you're seeing here is what remains of this unlucky star. Now, I'm going to play a movie. It's not a movie, this is actually a numerical simulation of the process. And what you have here, this blue thing is a black hole, should be seen. Then this little guy here is a star. So I'm gonna wait very fast first, but now let me take this thing back in time. Go back. Now I'm gonna do it slowly. There is a zoom in also. You can see the star gets close until it gets too close. And then it gets disrupted, and gravity of the black holes makes this matter blow up, and that's how we see those forces in the sky. That's one way we can produce these amazing brightenings in our sky. Option number two is if I'm a star, I'm born with my companion, and I happen to crash against my companion. Specifically, we can get the brightest displays if the two stars that are colliding are special ones, are neutron stars. Those are extremely dense stars. You can think about a neutron star as taking the mass of the sun and put it down in 7 miles of radius. That's what a neutron star is. What I'm going to play is a fake, well, not fake movie, I should say, an artistic rendering of the event. But the story is a true story. It's a true story that happened in 2017. I'm going to play the video. You can see there's a movie. The two neutron stars are orbiting each other. They're losing energy. I'm going to come back to this, why they're doing that, until they merge. There's a very violent collision that also releases an incredible amount of energy and can cause these rebrightenings in our skies. It's a very true story that changed astrophysics in 2017. It's the first time we captured light and gravitational waves. I'll tell you later about gravitational waves in human history, the first and only time so far. So how can I die? Third option, if I am a massive star, so if I'm at least 10 times the mass of the sun, then I will end my life with a huge firework, with a big stellar explosion. Again, this is an artistic rendering, so this is just art, but it will end on a true picture, and I will stop there. So for a star, the life of a star is a fight against gravity. You always fight to maintain yourself against gravity, but at some point, gravity wins. That's a law of the universe. Gravity wins. And at that point, stars explode. I was telling you that this image is actually a true image. And maybe if I take a better one like this, you will recognize this object in the sky. It's very famous. It's the Crab Nebula. And we are very sure that it was a star exploding because we had, well, not astronomers, but Chinese observers that could witness that explosion. And they told us in 1054, a new star appeared in the sky. This is an explosion in our own galaxy. And it was so bright that you could see it also during the day. 1,000 years ago. This is an optical image. So let me go now back here. So this is our menu of the main things that can produce these new lights in the sky. We are very used to speak and think in terms of visible wavelength. We have our own 2 detectors that can only pick up a visible radiation. These type of events are extreme. They produce radiation across the entire spectrum. And while maybe we don't experience radiation with eyes, we can experience it in other ways: radio, microwaves, infrared, UV, if you're growing some plants, X-rays, we see our bones, and unfortunately some gamma rays for some bad reason right there. So these events, they shine through the entire spectrum. Now, let me go back to our Crab Nebula, our explosion 1,000 years ago. This is how it looks if I look at it with visible frequencies. So this is a Hubble Space Telescope image. But if I could put on X-ray glasses, that's what I would see. So you can clearly see some structure. So you can see these little jets here. You can see some matter that is swirling around here. And this matter is extremely hot. And that's why it shines through X-rays. If you squint a little bit, that thing here, this white dot here, is a neutron star. Neutron stars are born from the death of big stars. So now, if I could combine one eye in the X-rays and one eye in the optical, that's how I would see the Crab Nebula. But there is more to this. So the Crab Nebula shines through the entire spectrum, and it does look different. Look, in the gamma rays is just a point source. Here we see those little jets, and then here we can see all of this structure. So it's just like when you have multiple people witnessing some event, everybody will come up with a different recollection of what happened, and you have to listen to all of them to put together the story and understand the truth, right? This is very much the same. That's the same what we do here. So each of these photons are important and precious because they tell us something different about the very same event. What we do is to collect them all and try to make sense of what they are telling us and understand the underlying physics. So if we go back to our 3 types of phenomena, I told you they shine through the entire spectrum with light, but they do something even more special. They also produce what we call gravitational waves and neutrinos. So let's talk for a second about gravitational waves. There are 4 fundamental forces, one of which is the electromagnetic force. One other of them is gravity, gravitational force. Gravitational waves are the same for gravity as what light or electromagnetic waves are for the electromagnetic force. So they are a manifestation of gravity. Neutrinos are tiny little particles that almost travel at the speed of light, and they don't interact with matter. They go through us all the time, for example, the neutrons from the sun. Why they're so important? Because both gravitational waves and neutrinos, they go through matter. So while you can close your door and stop light, you're not going to stop gravitational waves. You're not going to stop neutrinos. And that's very important because a lot of the phenomena that we want to study are so dense that light has no chance to come out. But gravitational waves and neutrinos can give me information about what's going on. They're our guides through darkness. That's how I look at them. So by now, you understand very well what is time domain astrophysics, is the study of this very violent phenomena in the universe. And by now, you also understand what is multi-messenger astrophysics. We combine light, neutrinos, gravitational waves, so multiple messengers to make sense of our universe. We're living through a very special time in human history when we can combine the three of them. Something that was not possible to do before 2015. I could not have said that in 2014, for example. Right, so why now? Now I told you a little bit about my time domain, beloved time domain astrophysics, but why now it is all happening? It's pretty much a consequence of a technological revolution. It is because we have this type of machineries that can take pictures of the sky every night, or if you're a radio person, you don't care about the sun, so you can also take pictures during the day. So what these things are doing is pretty much what I've asked you guys to do for me tonight, which is to spot new things happening in real time. But why we are finding new things? Every time you go and search for things is all about when you search and where you search for that precious thing, right? I'm going to give you a feeling of why this is a time of discovery. This is the only plot, I promise, where you have luminosity versus time. And our goal would be find this very fast transient. Transient is any of these lights that you saw at the beginning coming in and out. I want to detect that thing. In the past, meaning let's say 15 years ago, I could only take pictures at these 3 times. To understand that maybe I would have caught a little bit of a tail here, but I was hopeless. I could not see it. But now, since we can take many, many pictures, the game is easy. I have many, many pictures. I just need to ask myself what was there, what is there now that wasn't there 1 hour ago, right? The second half of the answer of why we are discovering new phenomena is about where we are looking for this. As humans, we love things that we think are beautiful. So if I show you this galaxy, that looks very pretty. But if I show you this other thing here, not that much, right? This is maybe my favorite galaxy in the universe. It is also a beautiful galaxy, but not as beautiful as this one. So what is happening is that now we can afford taking picture of the entire sky. I don't care if it looks good looking or not. I take a picture, and that allows us to find this new light everywhere. And it so happens that our universe likes weird places like this little tiny galaxy. Okay. A paradigm in astrophysics is that every single time we deploy a new capability, a new observational capability, we find new things. So that is always and always true. And we always find the unexpected. Even if we always pitch, okay, I need to be careful here because I'm on YouTube, right? So even if we always pitch things like we know this, and that, the truth is that the real engine is what we do not know. And the unexpected is way more interesting than the things that we can predict to find. The other second point of why now is a special time for multi-messenger astrophysics is because we can actually do it. We can actually understand how things happen through neutrinos and gravitational waves. So point number 1 is giving us discovery power. Point number 2, by combining all the messengers, is giving me the possibility to understand what's going on. And that's why this field has been recognized as the field, the primary discovery field, the decade in astrophysics. Okay. So this is my way to tell my students that's how we're filling up a big knowledge gap that we had. So by now, hopefully I convinced you that I do have the tools to find those new lights. You might be asking, who cares? Why would I care about a stellar explosion that happened before the dinosaurs were wandering this planet? And the answer is, you can live your life happily and probably it's okay. But let me give you my answer to this. I'm going to give you many answers. So first of all, these lights are so powerful that I can see very far in the universe. And depending on their brightness, I understand how far they are from me. I measure distances. And that's how we were actually able to discover that the universe is expanding. Option number 2, if you don't care about the universe expansion, is they produce these explosions, mergers, they produce the elements our bodies are made of. For example, our Earth has a large content of heavy metals because of these ones. And last week, we had a wonderful lecture about the universe nuts by Enrico about this. So if you didn't have the time to come here, please go and watch it on YouTube. And third reason, when I have a gigantic explosion, this is also releasing energy to the galaxy, is talking to the galaxy, and is also driving the evolution of the galaxy itself. And maybe even more fascinating, I showed you the Crab Nebula formed a neutron star in the center, right? So this is the way our universe uses to produce the most extreme objects, neutron stars and black holes, and those are the sources of those neutrinos and gravitational waves that we can now detect. So hopefully there is enough reasons to care about transients, even if not going to change our lives in terms of tomorrow's. Now, let's stop and think. So hopefully, I convinced you that I have the tool to do something. I have the intellectual motivation to do something, but let's get practical here. I want you to have a feeling for what do I do during my day? What do we really do? So I'm going to try to make my questions very concrete so you understand what I'm trying to do. And then I'm going to give you a feeling for what do I do during my day? So first of all, I'm going to focus on stellar explosions here for a second. We know the stars explode, and I can be extremely sure that this is happening. And I can be so sure that it's happening in our own galaxy, but also outside, for this very same reason. Let's look at that distant galaxy, and let's zoom in really a lot. So now we are seeing all of these are stars in this faraway galaxy. And something happens, and I see a very, very, very luminous display coming from that direction. And I wait a few months, and I take another picture of the same region of the sky. Maybe you have already seen what happened, but let me show you. This was before the big light. This is after. I'm sure that that star has exploded. Every single time I show this, I find it remarkable that we can actually say, oh, that star, no longer here, gone. I know that the stars explode, and so it might look like I know a lot. But actually, this seed of knowledge is surrounded, this island of knowledge is surrounded by a sea of ignorance, the good ignorance, the one that is the fuel of my research. I can't tell you what happened during the last moments of life of this star. I don't know. I can't answer that. I can't even tell you what that explosion has produced. For our own galaxy, I can see the neutron star, like the little dot. This is way too far away. There's no way for me to tell you what has produced. Those are very big and very basic questions, right? I don't know how I got there. I don't know what I left behind. Very simple questions, but fundamental questions. So how are we trying to answer to these questions? And the way we do it is as follows. We do have discovery engines, which is pretty much, again, what I asked you to do, spot the new light. And whenever they find something new, we call it trigger, new and interesting. We call it trigger. And that trigger gets passed on to our follow-up team here. I'm focusing on the transient extragalactic team at Berkeley. That's my team. And my fantastic postdocs, and grad students, and undergrads, they go and trigger all the possible facilities they can put their fingers on. No photon is left behind is our motto. We really want to collect all the information possible. So it's sort of cheated though, because we can't actually play this game of finding by eye sources. This is absolutely not tractable right now. I have maybe 100,000 things that are changing. I can't do it by eye. So any real discovery engine, modern discovery engine right now, it needs to have some component that has to do with artificial intelligence or intelligence or machine learning that tell us there is something new in that part of the sky and it's not an artifact, so you should care about. And the novelty in the past few years is that we are getting these alerts or triggers not only from the optical sky, also through gravitational waves. So here I put a link because you can actually be part of the game. So the way it works is that we have an app on our phone. I could not bring it here, but we have an app on our phone, and that rings whenever there is a black hole merging with another black hole in the universe. Black hole neutron stars, you can get paged. That's how we get the alert, and they tell us somewhere there is something new and you should go look at it. I always find it extremely exciting when my phone rings in the night and it's not my sister. But I know it depends on personalities. But look at, you can really know that a black hole has merged with another black hole far away in the universe. I find it fascinating, really fascinating. And again, if you want to be part of the game, it's there. Actually, to the young people in the audience. So now, let's see what we have done here. So let's play this game for this galaxy. Let's zoom in this galaxy. So we identify a transient. This was a little bit unfortunate. This transient got the name, AT is not written here, 2018 COW. We're not very creative. We start with AAA, AB, and this poor thing got COW. So if you hear astronomers say, how is the cow doing? That's what they mean. And so we understood it was a transient of interest. And so my team repointed all of these facilities. So we repointed 16 facilities on the ground. We triggered our fleet of a spacecraft, radio antennae, everything. Now, of course, it's not that these instruments are there being idle, right? They are taking observations with somebody else. So if you're interested, after this talk, I'm very happy to chat about the sociological implications of me interrupting my colleague and say, hey, stop, go on target, it's mine. So there are some implications here. All right, so that's what we did for our cow. Again, what do I want to do? I really want to take all of those photons and model them and understand the physics. That's what I want to do. So why I care so much? Because they can tell us something about what happened in the last 1,000 years. So I will try to convince you that we do actually have a time machine for free. So let's do it step by step. So first, we're gonna watch this movie. This is the sun. All I want you to focus on is ejections of mass. So there is mass that is lost at any point in the life of a star. The stars lose a lot of mass while they are before their death. And if you're a massive star, like 10 times the sun, that is way more severe as a process. Okay, so now we know that stars lose mass. So now let's simplify the experiment here. We are this star. Okay, we are this star here. And let's assume that during 3 times, I had 3 episodes of mass ejections. And the key word here is that these mass ejections are low. You might ask, how slow is low? Low is like 50 miles per second. That's low. But these are slow. We understand slow compared to what? So let's assume that one of my mass ejections, I'm the star, happened 1,000 years ago. One happened 100 years ago instead. And one happened only 10 years ago. now I reached the end of my life. Why does it happen? Because I had some fuel. Fuel for a star is hydrogen. I used nuclear reactions inside me to support myself against my own gravity. But at some point, I used up all of my hydrogen. It's game over. Gravity wins. And I explode. So the explosion, the front, is extremely fast. This is where the slow and fast come into play. The explosion front can be easily 500 times, 1,000 times faster than those mass ejections. So now, if I ask you, how long does it take for the explosion shock to reach my most recent mass ejection? Simple equation is around 7 days. So after 7 days after I exploded, the explosion shock has reached the first mass ejection. And when that happens, it glows, becomes more luminous. And of course, the explosion doesn't stop. And at some point, we reach our second mass ejection. How long does it take? Easy. Let's multiply times 10, it's around 2 months. Just like before, when I reach that density over density, I light up. So now you understand the game. I wait a little bit more. After 2 years, the shock front will be the front of my explosion, has reached the third of my mass ejections. And just like for anything else, I light up. So now you understand, if I'm a good astronomer and I keep taking data over 2 years, or just 2 years, so a time scale that is very human-like, I can actually go back in the life of a star all the way to 1,000 years ago. So by tracing this, I bright up, then down. I bright up and then down. I can reconstruct the life of a star in the last 1,000 years. This is a place where theory is not predictive. This is the only way we have to actually put the final pieces of the puzzle and understand what's going on. So I hope I very much convinced you that it was not like Back to the Future, but sort of, right? I can go back in the past of that star all the way to thousands of years ago. So, as I said, these explosions can be very luminous. And in the little exercise that I asked you to do, we're looking at a galaxy that is 50 million light years far. What that means is that I'm actually getting very old news, right? Because this is what was happening 50 million years ago. I'm seeing the universe how it was, not as it is. So it's always true that every time we look back, every time we look far away in the universe, we're also looking back in time. So this is another of these time machines that we're given for free. That's some complications when you start to do physics, but we are given this time machine for free, completely for free. So now we detected the supernova in 2020, but the supernova went off 50 million years ago. It's long gone, long gone. So this is tied to the other time machine I want to talk to you about tonight. Sometimes some particular type of explosions are very, very, very rare, but they can be extremely luminous, and they were discovered in the gamma ray sky. And it's not just by chance that they put here this picture, because gamma ray bursts have a very interesting history. The reason how, well, the first time we were trying to detect them, we were not really looking for astrophysical sources of gamma rays. We were looking for very much human sources of gamma rays, meaning nuclear experiments. That's why they're very related to this picture. The gamma ray bursts represent way less than 1% of the ways stars die. They are the most extremes of these stellar explosions. We do not exactly understand why this is happening, so why only a few of stars die this way. But when they shine in the gamma rays, they outshine the entire universe in gamma rays. It's absurd. In a matter of a few seconds, a gamma ray burst would give you more energy than the sun was going to give you during the entire lifetime. They are really extreme, really extreme. So gamma ray bursts have a very special place in my heart because that's where I started from as a PhD student. I was doing my thesis in Milan. I was working for the SWIFT spacecraft. It's a NASA spacecraft with Italian, UK, and US participation. And my job was to respond to alerts of gamma ray bursts. So first of all, they are detected in the gamma rays. So you need a spacecraft to detect them. Thankfully, they don't get all the way down to Earth. And my job was every time a gamma ray burst went off, I had 120 seconds, roughly, to get on a telecone. And I was responsible for one of the three instruments on Swift. And we had to go out the entire world with a position, meaning where to repoint. And we had to do it ASAP, where ASAP meant 10 minutes. At most, 15 minutes. It was as much as you could afford. Of course, the universe does not know what you're doing. So when I was on duty, this gamma burst could go off at any point during the day, at night, and which has an interesting impact on your social life. But my family got used to it. They accepted the fact that it was nothing to do. So, and that's why they are registered to the black hole merger app, so that they know not to bother me when that happens. So my job there was to release these alerts. And to give you an idea, so how many of these alerts would I get? Well, on average, is one every 3 days. Poisson statistics is very mean. It's very mean. And that means that during 24 hours, you can get 5. And the first one, you're very excited. The second one, I'm still very excited. The fifth one, less so, let's say that. But here is what happened on a day that I still remember. It was the 23rd of April, 2009. And we're not very creative. We call it GRB 090423. So this GRB went off from the gamma rays, was really nothing really exceptional, but we understood right away that this was a very distant source in our universe because it was not producing light in the visible, it was producing infrared light. So here, I put a histogram of all the distances of this gamma ray burst. This is a historical piece. Now we have some more here. And in this scale, you understand that the red guy is very far. Let's translate this scale into something we understand better. So now redshift 0 is now. So let's assume that, well, now the universe, let's say it's 13.7 billion years. So this gamma ray burst happened when the universe was just 0.6 billion years old. It's really, really when the universe was very young. To make it a little bit more concrete, if we think about the universe as an 80 years old man, this is my advisor. That's a tribute to my advisor, to whom I owe a lot. Well, this GRB happened when that man was only 3.5 years old. So we have these incredible opportunities to get these pictures of a very young universe for free. So maybe it's not like Back to the Future, but even better, right? We can see the very early universe. I see that my time is running out. So I hope I convinced you that time domain multi-messenger astrophysics is one of the frontiers of discovery that we have in the next decade. This is why we are starting a center at Berkeley. And together with my fantastic grad students, we will try to find the secrets of to decipher the secrets of our universe. So just to end, I study the end of things. I study how stars blow up. But it's actually, I'm understanding how we got there. And every time a star dies is the birth of a black hole, is the birth of a neutron star. Every end in the universe is a new beginning. And I want to leave you just by thanking you a lot for sharing with me your most precious thing, which is your time. Thank you so much.
Any questions? How will the Vera-Rubin telescope affect your research in the time domain astrophysics?
The question was how the Vera Rubin, which by the way, the Vera Rubin is sponsoring my water bottle. So how the Vera Rubin is going to help and how it's going to affect this investigation. The answer is in many, in gazillion ways. So within the Vera Rubin Observatory and the scientific collaborations, I'm leading the subgroup that is aiming at finding the counterparts to gravitational wave sources. And we actually just had a workshop and we submitted our recommendations to the project. Why? Because Vera Rubin, for context for everybody, Vera Rubin is a gigantic telescope in meter glass, so it can go extremely deep. But it combines that with very wide field of view, very big eyes. So think about that as, let's say, 8 degrees squared, so like 4 full moons. So why is this important? Because I can go deep and I can tile the sky very efficiently. So since when gravitational wave instrumentation detects something, they tell us something happened there, somewhere there, and we need to tile. And that's what Vera Rubin is going to do in an amazing way. This is just one example. Honestly, Vera Rubin is going to revolutionize this field. So thank you for that question. We should start getting science in the next year, so stay tuned.
Yeah. I wanted to ask you about transitions over time. A little unrelated, but so many of our physicists go from Berkeley to Harvard, to Milan, and Sloan. What's the impetus for those transitions?
So I did my thesis in Milan, and what I was looking for was for opportunities to lead my own projects, and US offered me that. And then I met my husband 2 years after, and that's why I'm here. That's what is the transition is about. Yeah. Yeah.
What is the physical mechanism for the passage of time?
Well, that's a multi-million-dollar question. Yeah. Yes. Sorry. The question is, what is the physics behind the transition of time? So that's a very amazing question. I think that we don't have a full answer to that. So technically, if you look at our equations, in most cases, I would say all cases, there is no reason why time, they are symmetric in terms of time. There is no reason why you could not go back. However, the quantity that is we know has a time error is entropy, which you can think about that as like disorder. It's called disorder, and that's so most physicists would answer to you connecting to the meaning of entropy, but there is no single answer that I can give you.
Yeah. So something I'm still trying to get my head around a little bit is we're looking at calculations based upon time distance, and at the source locations, we're looking at extremely dense with a lot of gravity. And I would keep wondering the effects of general relativity in making the calculations and the inferences.
Yes, so the question is about basically what are the effects of general relativity when I have signals that are coming from places where gravity is so strong. So the answer is that we are taking into account GR. We have to do it. So general relativity basically has influence on almost every aspect of what I told you, but let me pick one. So, we had that star that was wandering very, very, very close to the black hole. And I told you that this process makes matter glow, but I didn't go into many details. So one of the ways this is happening is because the star is wandering around the black hole, is getting shredded, and then there is a precession that is a consequence of GR. So all these streams that are the remaining of the stars intersect with each other. That's a consequence of GR. And that's one of the ways you can basically convert kinetic energy into heat, and heat is photons. This is just one of the examples. You understand, when I'm telling you this star is exploding, it's producing a black hole, I have to do GR there. There's no way I can't, yeah.
But that,
Building on that question, all your observations through those different senses of gamma rays, et cetera, are you able to actually find astrophysical algorithms, equations that predict the next? And is that a big part of what's happening too?
Okay, that's another excellent question. So the question is, based on my knowledge right now, can I predict when the next star is gonna blow off or alike? And the answer is that I wish. So we want to get there. If I could answer that question, it would imply that I really understand all the conditions for stellar explosions to happen, which is actually not the case. But we want to go there, and one of the goals is actually to try to trace what these stars are doing in the 10 years before, and trying to understand when maybe they will blow up. However, it's very true that by combining information across the spectrum, we are able to understand the physics of what is going on. It's very true. Here, I tell you the limitation. The true limitation is that photons, when we work only with photons, when the cases for we are forced to work only with photons, they can stop pretty easily. So they don't give you information about the cores of my explosion. They give you information about the skin. That's one of the challenges. That's why I hope for gravitational waves and neutrinos is for them, these special messengers, to give us information that is coming directly from the cores.
Sorry, yeah. Why do gravitational waves propagate at the speed of light? Stimulates this phenomenon, isn't it?
Yes, the question is why gravitational waves travel at the speed of light. That's our current understanding. We have nothing against that we could find observationally that would imply otherwise, even if people are looking for deviations from GR. The answer has a lot to do with the thing. It's a long answer. Can I give you the answer afterwards?
Yes.
It has to do with the mass of the particle or the lack of mass of the particle that is carrying it. Yeah.
Yeah, we sort of everyone's talking about light years, but you mentioned that light was only one of the very, very small paths that comes out. So how do you decide when something happened? We're only talking light years. What if you're reading a different kind of a way? Do they travel at different speeds?
Yeah, okay. The question is has to do with my units for distance, which is light years. So I'm using light years, honestly, because I'm talking to you, but I would never speak in light years. So light years just means the distance that is traveled by light over 1 year time scale. That's all. It's just a definition of a scale. But if I were to talk for work, I would speak in parsecs, which is a unit that we don't use in any other situation. Or maybe even more surprising, we speak centimeters. Astrophysics speaks centimeters, so I would tell you 10 to the 18 centimeters. And we speak grams too. I would tell you the mass of the sun in grams, which is not most intuitive. Yeah. So there is no reason. It's just a scale that I decided to use. Yeah.
Have you observed correlations between gamma ray bursts and gravitational waves?
Oh, fantastic. Thank you so much. Let's see if I have it. Yes, the question is about correlations between gamma ray bursts and gravitational waves. And the answer is a big yes. In 2017, I'm trying to go through the slides. I think I have the slide, but I don't know. So in 2017, maybe I don't have it. So I'll tell you the story. So in 2017, the reason why I told you that that event on 17th of August 2017 changed astrophysics is because the gamma ray bursts were known since 1973. And one of the ways to produce gamma ray bursts is merging two neutron stars. That collision of neutron stars that produce gamma ray bursts. So we knew that since 1973. And we also knew, thanks to our theorists, that collision of neutron stars would give rise to emission in the light basically. So on August 2017, we got an alert. I was still living in Chicago back then. I got an alert on my phone in the morning. And after a few minutes, we got another alert from the gamma ray space missions that told us that 2 seconds after the gravitational wave, there was a gamma ray burst in the same direction in the sky. So this is the first detection of light that is connected with the gravitational wave event. So now I can stand here and very confidently tell you that neutron stars collisions that produce gravitational waves, they do produce gamma rays, and we call them gamma ray bursts, short gamma ray bursts to be precise. Yes, and that changed astrophysics forever.
Do any of the events that you're monitoring show up on the LIGO?
Okay, so LIGO, the only event that for which we could connect my light with LIGO is that event in 2017. We keep trying, though. It's not that we're not trying. We keep trying and look for light coming from LIGO events. LIGO is a gravitational wave interferometer that detects gravitational waves. And right now, the challenge is that these events that I'm talking about are extremely rare intrinsically. So the universe doesn't produce that many. So LIGO has been on for a while, but we were only capable of detecting a neutron star merger with light once. That's why I always have the phone in my pocket. And a lot of you are, yeah.
I know the sun is not like as massive as other stars that may have these interactions, but how can observations from our sun kind of help with your research?
Yeah, in many ways. The question is, okay, the sun is a small star. For astrophysical standards, it's like a okay star. And because I just like those as blow up. I like, so you need to be like 8 to 10 times the sun to explode. And those are the ones that I really love. But the sun is not going to end that way. It's going to just end its life in a more quiet way. It's going to become a white dwarf. So how can the sun help me? In many, many different ways. I'll give you an example. So a lot of the physics that I do, when I told you the front of the explosion blows up when it encounters mass, what I was telling you is that I have a shock wave. That shock wave accelerates particles. Those particles emit X-ray and radio. It's a plasma that produces that radiation. And I can learn a lot about plasma physics based on what is happening in the sun. Just one of the many, many, many examples of what we can learn from our own star. Physics is the same. Isn't that beautiful? I can take physics from the sun and take it far away. It's always the same.
Folks, I see there was a more question, but then time is up. So if you can thank the speaker again.
Thank you so much. Thank you.